Hello, everyone. Welcome to Astronomy 103. And we're moving out of stars and talking about galaxies. So the first lesson, just like the first time we started talking about stars, we started talking about our sun, our local star. We're going to talk about our local galaxy now. So our galaxy is called the Milky Way. And today we're going to talk about what a galaxy is, how big ours is, and how we know its size and rough shape. And we're also going to introduce this idea of standard candles, how we're going to get the brightness of galaxies. So let's start by observations, the ones you can do by yourself. So if you go out to the country, you might notice a band of light stretching across the sky. And this has had a number of names throughout different cultures. And we, English-speaking Americans, call it the Milky Way. And this comes from the Greek word galactus. In fact, the word galaxy comes from the Greek word for milk. The first telescopes showed that that band of kind of faint light was actually a bunch of stars that were too faint to see on their own, but were bright enough in aggregate to produce this kind of faint band of light. And astronomers noticed that there were a lot more stars in that kind of band of light circling the sky, and there were a lot more nebulae in those directions. But it's hard to see the shape of the whole thing when you're inside it. It's like being in a forest. You can notice that there's not that many trees above you. There's only one layer of trees above you, and there's no trees below you. But if you look in all directions, unless you're near a clearing or the edge of the forest, you just see trees, more trees. Some trees are near you, some trees are far. You don't see the edge. So that's the dilemma we are in when mapping a map of the Milky Way. And it's also why we didn't realize that other galaxies were other galaxies. So the first person to try was a fellow named William Herschel. He's most famous for discovering Uranus. And his reasoning was, okay, I'll just assume all the stars are the same luminosity, so the fainter ones are just farther away from us. And I'll use that to make kind of a map. And he got something like the blob on the top. And he noticed that there were a lot more stars in the direction of the Milky Way than not in the direction of the Milky Way. Meant that our sun was kind of in the middle of a blobby disk of stars. So it was kind of a flat blob of stars. The sun was roughly in the center. And one of the historical lessons of the history of astronomy is whenever you get that the observer, humans, Earth, the sun, is in the center of something, it's probably not the actual center. It is probably due to some observational effect. And for the Milky Way, the observational effect is that we see all these clouds, these nebulae, these clouds of gas and dust, and some of them are bright, and some of them are dark, and the dark ones are blocking all the stars behind them. Just like we talked about with forming stars, a lot of the cooler, darker nebulas absorb starlight, and we can't see through them. So William Herschel was kind of stuck. He couldn't see that far. He could see that the galaxy had an upper edge and a lower edge from our point of view, but he couldn't see like the left, right, top, or north, south, east, west thing. And I'm making up directions here. So astronomers were trying to come up with a plan. Now, when we talked about star formation, we said, well, you can just use other wavelengths of light. Well, before the space program and the development of radio astronomy, you couldn't do that. We didn't have the technology. Or we had the technology, but we were trapped in an atmosphere that we needed rockets to get out of. They were looking for things that we could see that would show some sign of, that would not be as blocked by the gas and dust. And one thing they noticed was these globular clusters. So I mentioned them when we talked about star clusters. Open clusters are the young clusters. They used to be in star forming regions. They shed their gas, and now they're just a cluster of relatively young stars. Globular clusters are much older. They're, the one we talked about was 13 billion years old, and they mostly seem to hang out above or below the Milky Way. One of the other traits of globular clusters is that they are unevenly distributed in the sky. And it's not because they all hang out in the Milky Way, because I said they're above and below. There's a lot more in the direction of sky we see during the evening in like July and August than during December and January. So that astronomers were like, that's interesting. They're clearly asymmetric. What if we made a map of that? Now the problem is we can measure the directions pretty easily. We have maps of sky that show all the globular clusters we found, but they're too far away to measure their distance from parallax. Now, the other methods we talked about for distance was one thing you can do is if main sequence stars, they're pretty consistent. If you know their spectral type, how hot they are, you can measure their luminosities. And you can do this for star clusters. So this is an HR diagram of two star clusters, the Pleiades and the Hyades, and just showing their main sequences. And the bottom is surface temperature, spectral type. Top is the apparent brightness, not the luminosity. Because we know all these star clusters, all the stars in each cluster, all the stars in the red cluster, all the stars in the blue cluster, are all at the same distance, we can get by with apparent brightness and just say, okay, there's a little shift up and down. So what we can do is make an HR diagram, only worry about the main sequence, take our reference HR diagram, slide it up and down until we get the luminosity of the main sequence, and then get a distance from that. And we do this with the entire main sequence, not just a few stars, because when you do measure more stars, you're less likely to get messed up by errors. So we could do this with globular clusters, only there's a problem. The globular clusters are really old. Young open clusters like the Pleiades and the Hyades, they still have a lot of their bright stars are still on the main sequence. A lot of their big massive stars are still on the main sequence, so we can see them pretty easily. But globular clusters are really old. The only stars still on the main sequence are stars much less massive than the sun. Most of the bright stars you see are red giants, and those aren't as amenable to this. So we want to find something a bit brighter than the main sequence to fit. So we need to find something where we know the luminosity of it. And we call these kind of stars a star where we know the luminosity without finding its apparent brightness and distance, or in particular without finding its distance. A standard candle, it's basically a reference. It's this star is always this bright, this luminosity, so we can use it to measure a distance. It's kind of like a ruler, or rather it's kind of like a scale bar on a diagram. So we found some. So there's two types of stars we're going to talk about. These are all pulsating stars. So these stars are fusing helium to carbon, and they're in a part of the HR diagram we call the instability strip. That equilibrium between thermal pressure outward, gravity inward is really sensitive there. So instead of the stars sitting at a nice even size and temperature, they pulsate in and outward, and their size and temperature change slightly. And so they're kind of like they're breathing very slowly. And this means their brightness changes. And it turns out, well, you can determine the luminosity of the star from how long its pulsations take. Now, how we know this is from an astronomer named Henrietta Leavitt, who is working on the Large Magellanic Cloud. This is a galaxy, a nearby galaxy that orbits our Milky Way. It's smaller than us. And she was looking and discovered these Cepheid variable stars in the LMC. And she noticed that the ones that pulsated more slowly looked brighter in her pictures than the ones that pulsated more quickly. Now, she correctly assumed they're all about the same distance from the sun. The ones that pulsate more slowly must be more luminous than the ones that pulsate quickly. So she reasoned we could kind of if we can find some nearby examples, ones that are close enough to use parallax or another method to get their distances, then if we find one that's in a cluster too far away to use parallax, or in like the LMC, we can use that to get a distance to that cluster or galaxy. So our Lyrae stars, they all have about the same brightness. They all have really short periods. Cepheid variables have periods from anywhere from 3 to 100 days. And we name these, again, after the first ones we found. So RR Lyrae stars are named after RR Lyrae. Cepheid variables are named after Delta Cephei. So, all right, we now have a tool to measure the distances to globular clusters. We can just find some variable stars in them of these particular types. We have a distance. We have the other two. We have its direction. We can make a map. So this was done by a fellow named Harlow Shapley, who was kind of in a debate in the early 20th century. He was debating with another astronomer, are these spiral-shaped fuzzy objects we see in our sky, like the one behind me, are they other galaxies? Are they? Now Shapley was both people in this debate were kind of both right and both wrong. Shapley said, no, those are not other galaxies because the Milky Way is really, really big. And the other guy was like, no, the Milky Way is pretty small. You know, we could totally have other Milky Way sized objects in the universe. And the thing is, they were both right and both wrong. Shapley was right. The Milky Way is really big. But Shapley was wrong that you couldn't have similarly sized objects just really far away. Shapley was both astronomers were vastly underestimating the size of the universe. So, all right, let's look at what Shapley found, because he was using these globular clusters to argue this. What they noticed is that because of that asymmetry, once we got the distances to these globular clusters, they were centered on a region that's about 8,000 parsecs, say 26,000 light years from the sun, in the direction of the constellation Sagittarius. Now, this is also a part of the Milky Way that has a lot of those pretty gas nebulas and dust clouds and stars and all kinds of stuff. I had a picture of a region near there on the mapping slide. So this let us kind of estimate the size of the Milky Way. You know, we could now, and once we got space telescopes and radio telescopes and all kinds of stuff, we can make a more detailed picture. So from this, we discovered that we live in a cloud of gas and dust and stars. We call it the Milky Way, and we decided objects like the Milky Way are named galaxies. Ours is about 30,000 parsecs, or 100,000 light years across from one side to the other, and it's a flat disk. It's only maybe 2,000 light years wide, but it's 100,000 light years across. You know, just like our solar system, it's pretty flat. Now there's a bulge in the center, and that bulge is bar-shaped. And it's also surrounded by this halo of some stars, very few, and the globular clusters that we use to kind of identify the center. So here you can see a bunch of the pictures. You can see drawing of our galaxy in terms of, you know, front and side views showing the spiral arms, which we're going to talk more about on a few lectures, the bulge where the sun is, and, you know, that our galaxy is kind of roughly disc-shaped. It's much flatter in one direction than the other two. And again, when we look at it from the side, the bulge kind of bulges out a bit. The disk is relatively flat, and it's surrounded by this spherical halo that includes the globular clusters. So, in summary, a galaxy, it's a collection of stars and nebulae. And one more thing we're going to talk about next week, or next time, dark matter. Galaxies are relatively large compared to the other stuff we're doing. They're 100,000 light years across, and our Milky Way is not the biggest, though it's relatively big. We can estimate size and shape of the galaxy based on trying to find things other than stars, because stars a lot of times are blocked by gas and dust. And to give distances for things, we do look at the stars. We look for stars that are standard candles. We look for stars where we know their luminosity by some mean other than their distance. So next class, we're going to talk about the mass of the galaxy and introduce this idea of dark matter, which is really kind of weird and wonderful. All right, I'll see you then.